Today we shall discuss about the non-stationary states of harmonic oscillator. Non-stationary states of linear harmonic oscillator. Earlier we have solved time-independent Schrödinger equation for the harmonic oscillator, which is for 1D harmonic oscillator. This is 2 d2 phi n of x dx2 plus half m omega square x square phi n of x is equal to en phi n of x, where this en is n plus half h cross omega, and the wave function phi n is known to be phi n is given in terms of some normalization constant e to the power minus alpha square x square by 2 times hn of alpha x, where alpha square is the scaling parameter m omega by h cross. Now the time-dependent Schrödinger equation, the corresponding time-dependent Schrödinger equation is minus h line square by twice m del 2 phi n of xt del x2 plus half m omega square x square phi n of xt I h cross del t of phi n of xt. Since the potential does not depend on time, we can decouple this time dependent function as this is the solution of time independent Schrödinger equation, and e to the power I n t upon h cross. This is the time dependent solution of Schrödinger equation for a given value of n. In general, we construct the general solution of this time dependent equation is phi n of xt is equal to summation over n is equal to 0 to infinity cn phi n of xt. So to say this is and if we write it as e to the power minus en t upon h cross, this sum extends from n is equal to 0 to infinity. In reality, it is not possible to include all the steps. However, first let me come to the normalization of it. If we write the normalization in integral form, it is psi of xt psi of xt dx from minus infinity to plus infinity. This should be 1, that is the normalization. If we write this in the Dirac bracket notation, it is this is the corresponding relation in Dirac's notation. This closure of the bracket means that the integration of the space variable is implied. Now, for this, we write m index. So Cn. Then comes the time dependent part. For this state, that is psi star e to the power, it is e to the power I em t by h cross with a plus sign, because we are taking the complex conjugation, and it is plus en t upon h cross. Now the space dependent part. Phi m star of x, phi n of x dx from minus infinity to plus infinity. This is delta mn. So once sum goes, so we have only sum, say, over n is equal to 0 to infinity, then it is Cn, so it is Cn modulus square e to the power I em minus en t by h cross. When m is equal to n, this term goes, and this is also 1, so this is the result. So this is the completeness. If we want to do the same calculation using Bryant notation, the result is like this. This is m sum from this term. Then this is delta function, so the result is n is equal to 0 to infinity Cn modulus square. The result, in this case we need to write less amount of quantities, because many thing is implied over there. Now we calculate the expectation value of x in such a state. So these are about the normalization, and we see the expectation value of x. In this case, as we shall see that the expectation value of x will have time dependence. So let me write the general state. Now the expectation value of x. X operator in this state, so we write it as we shall see, it will have time dependence, so we write this. I am using Dirac notation. For this part, summation over m is equal to 0 to infinity Cm star e to the power plus I emt upon h cross. Then from this part, n is equal to 0 to infinity Cn e to the power minus I en t upon h cross. Then it is phi m phi n. Oh, sorry. This is our knowledge on the calculation of expectation values sees that the only allowed values is m is equal to plus minus 1. We can even write it in a simpler way as mxn. So the m sum goes and we will have only two allowed values of m, that is to write sum over n is equal to 0 to infinity. First thing, it is n plus 1 star cn. M is equal to n plus 1. In that case, the energy value is e to the power em minus en t by h cross. This becomes e to the power I m minus n t by h cross, as en is equal to n plus half h cross omega. So we write it as e to the power I omega t times n plus 1 x n. This is the first term, and second term plus cn minus 1 star cn e to the power, in this case m is n minus 1, so it will be minus I omega t, and this is n minus 1 x n. We know that the q in terms of q is equal to alpha x, so x is equal to q by alpha. So we remember that this element is 1 by alpha times n plus 1 by 2, and this element is 1 by alpha times root n by 2. So we write it as sum over n is equal to 0 to infinity. This entire thing except this is written as an e to the power I omega t, and entire things except this is written as bn e to the power minus I omega t, where we define an as cn plus 1 star cn and bn we define as so this can be written as summation over n is equal to 0 to infinity cn sine omega t plus delta n, where delta is a phase. It is very easy to connect AB with C, say as C square is equal to n square plus bn square, and so on and so forth. So we see that when we carry out the expectation value of x in a non-stationary state, or which is a superposition of non-stationary states of the harmonic oscillator, the expectation value oscillates as in the case of classical oscillator. This is an oscillation, simple harmonic oscillation with frequency omega and phase is delta. So again this expectation value behaves as if the classical oscillators. Now I come to another aspect. We have constructed the wave packet. This is actually the wave packet. This is the wave packet, and if we find the probability density of the wave packet, then we know that we calculate rho. Then this is the wave packet, harmonic oscillator wave packet. So the rho, if we calculate rho, it will be an x function of x and t, and it is psi star xt psi of xt. No integration is there, so it is a double sum. Since a function is real in this case, it hardly matters. So if we write it, this is time dependent. That is another reason of saying it to be the non-stationary state. It is time dependent one. But one problem is that when we want to execute this in reality, it is not possible to consider this large number of terms, infinite number of terms. So what one does, one restricts the sum small n from 0 to capital N, and we get a real life expansion, and that expansion we define as this: phi phi n of xt is equal to summation over n is equal to 0 to capital N. This is this capital N, Cn phi n of x e to the power minus I e n t by h cross, in which case the corresponding position probability density will come out to be everything. This sum extends from 0 to infinity. The sum will extend from 0 to n. Omega t. If we want to normalize this, that we want that this wave function we have we make include 2 terms in it or 3 terms, whatever may be, we want to make the wave function normalized. So the normalization condition in that case, normalization as we have done it is summation over n is equal to 0 to capital N Cn modulus square. These Cn's are different for different states. We make a very simple assumption. That is, all Cn's are equal to 1 by root n. In which case, this gives you 1. In that case, this equation with such simple assumption becomes and the corresponding row n of xt becomes 1 by n rho n 1 by n summation over n from 0 to n phi m star phi n phi m star of x phi n of x e to the power plus I m minus n omega t. This is a representation of the wave packet. In the class note, in the study material that has been provided to with you, we have considered few values of n is equal to 2, 3, 4 and 5. 4 cases has been compared. You will find that with the increase of values of capital N, the width of the wave packet decreases. It decreases with n. So as we increase n, this width decreases and height increases. And furthermore, one thing that we have plotted for all these cases, the time interval t is equal to 2 pi by omega has been splitted into 8 intervals. That is, we have plotted this with t by 8, or t is equal to t by 8, t1, t2 is equal to 2t by 8 and so on and so forth. At T9, the shape of the wave packet becomes the same. It will be seen that with the passage of time, if we consider this is the middle point and this is the classical limit minus x and this is plus x, with the passage of time, this wave packet, say we have this form, then it moves in this direction and goes. Then after a time it spreads out and then it goes like this, then it starts moving in this direction, and with the passage of time this wave packet oscillates back and forth between this region. That's all about the wave packet description of harmonic oscillator wave function. You may consult any suitable video which is available in the net. I will show you one. I will show you one such that I have been constructed using a PowerPoint presentation.